Welcome back to the SEMIVA seminar on Spectral Algebraic Geometry. Our speaker for today is Krishna Kumar, and he will give us an introduction to the word of Spectral Algebraic Geometry. So please, Krishna, stage is yours.
Thank you, Federico. So I first of all have to thank everyone, like the organizers, for giving me this chance to present this introductory talk, because firstly, it sort of creates a good atmosphere to follow the seminar. And most importantly for me, it was very useful to know many of the underlying topics that we are going to see in this seminar. So in a way, it is highly beneficial for me to take this talk so that I can prepare more on the background. So with this in mind, so I've tried to make this talk as grassroots level as possible in order to be accessible to non-experts. And so the flow of the talk is going to be just a bunch of definitions, but also put in a more cohesive way. And also we'll see a lot of examples in the run through. And at the end, we'll finish it off with some kind of speculations of what we could expect from the following talks, right? So I'll start with this quote from Pierre Deligne, which sort of conceptualized this whole talk, which is like an absence of proof is challenge. But if you don't have a definition to begin with, it's already very deadly, right? So with this spirit, we'll have a good look on this talk, right? So before going into anything further, I'd like to say that if you have some questions, please do raise your hands, and also raise your voices. So if some notations is not clear, because we're going to abuse a lot of notations here with the normal categorical and infinity categorical way, right? So, okay. So we have this notion of scheme, which is a paired, it's a ringed space, comes with a pair. So it has X and it has OX, which is called the structure sheaf, right? So one can study sort of two independent theories. So one is like you can just enhance the structure sheaf and build up a new theory. The other way, we can also enhance just the topological space. You can just enhance more spaces, like advanced spaces, and you have a very different theory. So sort of both these theory have they have two different view deeply, but then they both sort of join together to give a very nice object that behaves as a very good representative objects for many of the algebra geometric questions that we would like to answer, right? So so briefly, I would like to go through this flow diagram. So if you just enhance, a scheme as a sheaf of commutative rings, which is like a very doesn't have any homotopic data. It's just like a very discrete kind of, in terms of spectrum, it's just discrete. We'll see what it is as well. And then so we can sort of impose a structure, more advanced structure on these rings, which is called the sheaf of which is called the infinity ring. So once we have this infinity ring, we can see how we can sort of play with the homotopies that come attached with this ring, right? So what does this look locally? So locally, we'll see it is going to be a spectrum of an infinity ring. We'll define what it is, and we'll see these would be exactly the affine kind of objects in this world. And there's of course like a gluing criteria that will give us a global object, which we'll call as a spectral scheme. And of course, the category of schemes is a full subcategory of this. So in a sense, we also sort of this theory encompasses also the category of schemes and the theory that lies attached to schemes, right? And then there is this connecting object here that sort of connects us to the main object of study of this talk today, which is the Spectral Deligne-Mumford stacks. And if we just go to the other side of the story, we have topological spaces, and then one can sort of equip this topological spaces into an infinity categorical structure, which is so-called the infinity topos, which is characterized by pre-sheaves on certain Grothendieck topology, right? So what does the local object look like? So they're going to be like denoted as SpecR. So I'm sure we're all familiar with SpecR, which is the spectrum of ring, but this is a spectrum of a ring, but the ring is still a commutative ring, but then the topology is it's an étale topology. So in a sense, it is more sort of finer than the Zariski one. And then the global object that we would like to have is, of course, the Deligne-Mumford stack. And of course, the scheme is contained in this category, so that we also see this as an enhancement of the category of schemes. So there is a connecting bridge that connects this theory of DM stacks with the object that we want to study. So in this way, we see how very sort of two different worlds sort of combining to give a very rich and enriched object that allows us to answer Tannaka duality, as is the main topic of our seminar. So I would like to call these series of definitions as a base course. So it's going to be a crash course. I'm not going to sort of dwell on each and every detail because it's something that we would have already seen. It's just a fresh recap, right? So we'll talk about grothendieck topologies. So mainly about Zariski and et al. Topology. So a site is a pair of a small category usually and a grothendieck topology. So grothendieck topology is like it's a topology, but sort of like usual topology has open sets, and grothendieck topology has open maps declared as open sets. And we will talk about covering a given scheme with respect to these maps, right? So grothendieck topology is something. So it is given by this covering of a given. So x if S is a category of scheme, as x would be a scheme, K scheme, and then it's given by this set of coverings that sort of has to obey these three criterions. And for example, the very simplest one is the Zariski topology, which is just a family of open immersions, and et al. Is of course et al. Maps which are smooth and unramified, right? So there are many variants that people want to equip this topology with so as to study many representative problems. So depending upon the nature we need. So this is in the decreasing order of fineness of the covers. So we have FPQC, FPPF, et al., big et al., small et al. You have Nishnevich, you have the big Zariski, and of course the small Zariski site, right? So and then what are infinity categories? So we are going to keep exploring this word infinity category throughout this whole talk. So it's better to have a good notion of what infinity category is. So let me begin by saying what is not this infinity cats. So by infinity cats, we don't mean any sort of cats in this. So it's just a very lazy way of writing infinity category, right? And then it is not a category which has a different notion of infinity. So we're not going to talk about infinity, so the real numbers and complex numbers are different infinities. So there's no business of that sort. So instead, an infinity category would be a notion of sort of having a higher maps, which has inverse up to some higher homotopy. So we'll see what this exactly means in a second, right? And first of all, what is the motivation for infinity category? So there is this theory called higher category theory, which sort of the motto is to sort of study category with higher morphisms, so-called N morphisms. So in order to study this, we sort of need a model to do this. So there are so many like Siegel categories, topological categories, and infinity categories. One of the model to study higher category theory. And then, so if you want to put this whole thing into a heuristic, we can sum it up like this. So a higher category theory is something which consists of its ordinary category theory, but then we also have invertible maps which are defined up to some kind of homotopy. Here it would be like termed as coherent homotopies. Okay. So there are different variants depending upon what we need. So infinity n would mean that all the morphisms greater than n are invertible. And similarly, 1 would mean all the morphisms greater than 1 are invertible. So this would be the ideal case for all the categories that we would consider on this talk. And for example, as a special subcase, if everything is invertible, every morphism is invertible, it's called a groupoid. So for example, group is a groupoid with a single object. So it's the most canonical example. And then, so quickly going through the data of an N category. So it has this kind of, it has an object, which is just X, Y, and Z. And then between objects, there are maps, so this part we're all already familiar with, like basic set theory clarifies it, right? And then, so between maps, we sort of have maps between them. So this is sort of called the two morphisms. In other words, it's a homotopy data between two given maps. So this also might be sort of familiar to people who are almost exposed to topology. So what happens after this is a mystery somehow. So there are three morphisms which are given by this kind of cube. The data is that so it is a data that makes all the 6 faces of the cubes homotopic. So this is also can be called as an homotopy between homotopies, right? And then one of the important constructions that people do in this setting is taking a nerve of a category. So nerve is sort of so once we have a category, then the nerve of the category gives you a simplicial set attached to it. So in a sense, that nerve is also adjoint to the homotopy category. So you have a category, then you can take the homotopy category of it, and the nerve construction is exactly the adjoint of this construction, right? So one main theme is like if you're given a category and then you take a nerve of it, then it's exactly like how nerves runs into a human body. So it sort of like decomposes each of the category, decomposes the category into each of the like components, like it has objects, one morphism, two morphism, and everything. And then so naturally one can sort of identify two objects attached to this infinity categorical setting. One is that we have a simplicial set, then we can ask when is the simplicial set a can complex. So can complex doesn't mean a chain complex, it's just a simplicial set. So just to make things clear, so a can complex is given by this data. So if we can find an extension to this map, it doesn't have to be unique, but just any extension would do. Also for including the outer horns, if we can find such an extension, then K is called a can complex. This is on one side. On the other side, if we have there is this great idea that given a simplicial set, you can sort of see it as a nerve of some small category. So this occurs if and only if this map can be extended uniquely via this map, and this has to be true for all the inner horns. So these two somehow like sort of are two different kind of worlds, and infinity category is sort of like a good bargain between these two worlds, in a sense that we just need a map, doesn't have to be unique, but we just need it for the inner horns, not for the outer horns. So this is exactly the definition of infinity category. So it is a simplicial set such that what we have said here exactly that holds. Like, so there is an extension, and it also all for the inner horns, right? So every ordinary category is an infinity category because there is no higher data, it's just trivial. And every can complex is an infinity category. For example, we have the singular construction of a topological space. It's a very natural construction of getting a simplicial set out of a topological space. That is an infinity category. And then taking a nerve of a category is also an infinity category, right? So that being said about the infinity category, we'll go to this notion of E infinity ring. What is this E infinity anyway? So for me, personally, when I saw it the first time, I thought it's a ring, but then it's not a ring. It's actually more than a ring. It's a series of rings somehow. So it can be put as a spectrum. We'll see what it is. So it's a comical interpretation of how I saw this definitions, like when I Googled it. So this E infinity rings could be called as a richer version of ordinary commutative rings. Okay, that's not harmful. It's okay. So other version is like you can see it as a commutative monad in the stable infinity category of spectra. This is somehow not so clear, at least to me in the beginning. And then harsh definition would be like it's an A infinity ring, but it's also commutative up to coherent homotopy. So this actually like no way to decrypt this at the first go, right? So we'll see what it is like exactly in this next slides. So E infinity ring actually stands for a E infinity ring spectrum. So it's not just an ordinary ring, but a spectrum also equipped with the ring structure. So there's going to be a multiplication map that gives the spectrum a ring structure. So these are sort of basic elements to study in a stable homotopy theory. And so E infinity rings are also called as highly structured ring spectra, right? Like in the literature, you can find these words. So before beginning, there are two good things to know about this. So what the stable world, like the infinity version of stable world does is like it sort of axiomatizes the classical stable homotopy theory. So in particular, we use this strong criteria that every pullback is also a push out. So every fiber is also a co-fiber. We impose this condition. We'll see this one. And having a notion of stable infinity category is a very good way sort of smoothly correlating between the topological space and the chain complexes, right? So quickly describing what is a spectrum. A spectrum can be defined as the following data. So for every n in natural number, we have this space. So by space, I mean it can be a simplicial set, can be a topological space, can be an abelian sheaf of abelian groups, chain complexes, any nice thing, CW complexes, anything. So this is given by the sequence, and for every n, there is this map going between xn and xn plus 1, which is called a suspension. So and then given two spectra, then we can sort of define what is a morphism between two spectra by get this data here. So each of these ENs are called the bonding maps. And the condition is that this square should commute like at every stage. So first to see examples of suspension spectra. So given any topological space, so we can associate a spectra to it, which is called we're just taking this nth suspension. So this notation actually means that you take the nth sphere and then smash x with the nth sphere. So you get a suspension spectrum. And then the most natural example is the sphere spectrum, which is you just replace x by S naught, which is the disjoint unit of 2 points, the zero sphere, and then sort of build the spectrum. So you get S naught, S1, S2, S3. So this is like this follows from the sphere suspension isomorphism. So as a particular case, a sphere spectrum, in a sphere spectrum, each of this map is actually an isomorphism. And then it's denoted by this 1, which sort of secretly means that it's going to be the unit in the stable infinity category of spectra. And then there is this important inquisitive example of Eilenberg-MacLane spectrum. So which is like, I'm not going to define what it is, but one of the important property attached to this spectrum is that it exactly has homotopy groups only when I is n, like only at the stage n it has homotopy and it vanishes everywhere else. So we can see this as a building blocks for many of the constructions in homotopy, for example, to build a Postnikov tower construction and things like that, right? So there's a loose pathway. You start with CW complex, finite CW complexes, pointed, and then how do you go to spectra? So why I want to end with spectra is like the spectra is somehow the main object that is underlying all this construction that we are going to see in this talk, in the upcoming talks. So start with the finite CW complexes, and then we can consider the stable homotopy. Okay, there's a typo here, it should be ST. So just take the stable classes of maps between them. So there are two versions of homotopy. One is like the unstable and the stable version. In the unstable version, you don't sort of like have a good structure or good control of what the outcome might be. So in particular, you might not have a group structure, you might not have an abelian structure in whatever sense that you wish to have. So people study stable homotopy theory, which because it's more structured and hence it's also very easy to compute, right? So given two CW complexes, you sort of classify them up to the stable class, and then we go to this category of stable homotopy groups, and then instead of taking positive suspensions, one could also consider negative suspensions. So for example, here this n is restricted to a natural number, so you could also extend this to integers, and then we get a n-last category, so which is called the Spanier-Whitehead category, and then take the infinity categorical version of this. So we go to the category of finite spectra which are pointed, and then so we'll see that this is not enough for many of the representation questions that we need to have. So what people usually do is like you take a sort of a formal completion with respect to filtered colimits, and then it's called the int completion. So we get the final object, which is called the infinity category of spectra. All right. So this is just saying that all these facts exactly say that stable homotopy theory is more sort of structured and concrete than the unstable one. So we have more sort of control. All right. So there's this Spanier-Whitehead category that we talked about. So it sort of includes formal D-suspensions. So D-suspension is also called loopings. So in classical sense, there is this adjunction between, like, you have the loop spaces and then you have the adjunct spaces. So loop is right adjoint to taking smash product, and in other words, taking suspension. So it also holds in the infinity world, right? And then so one can see this SP fin star as sort of, you have this spectra of finite spectra, but you also sort of invert this suspension. So this is, I mean, so the Spanier-Whitehead category can be seen as it can be realized as this limit of this functors here, given this maps between this homotopy classes given by this map. So by formally inverting this, we get this category of finite spectra, and so we'll see in a bit how to change this into a spectra of into an object that we actually wanted to study, right? So all these objects, like they sit in a very natural environment, which is called the stable infinity category. And this category is defined as follows. So any infinity category is said to be stable if it has a notion of a zero object in particular. So this zero object is nothing but it's both initial and final at the same time. So objects into it and object out of it is very unique. The map is it's a very unique map. Okay? And if C admits all the finite limits and finite colimits, in other words, you should have all the fiber products and also the pushouts. And the suspension functor is an equivalence of infinity categories. So in other words, the loop functor is also an infinite. It should also be an equivalence of infinity categories. So there are two versions of putting this point down, which is like, so people call this a triangle. So a diagram of this sort is called triangle, having this zero object here. So for stable infinity category, fiber sequence is a sequence is a fiber sequence if and only if it is also a co-fiber sequence. So this sort of gives a more structure and control to what we sort of need to identify. So as I said before, there is this defect with having just taking the finite spectra. And so people consider this end completion, which is like the formal way of adding arbitrary colimits. So here we just mentioned that it only admits finite and finite colimits and finite limits. So by just taking this incompletion, we get this object called category of spectra, which also has it has arbitrary many limits. It is closed into arbitrary many limits and arbitrary colimits. Right. So this is one of the basic notions that we'll keep repeating in the seminar, which is like, given a spectrum, how do you associate a homotopy group to it? So given arbitrary spectrum E, then so we can define the homotopy group attached to E by this description here. So you take the home between the sphere spectrum and E, like in the category of spectra, which is exactly the connected component of mapping space between these two objects, right? So we'll see that it has some structure of an abelian group, and in particular, one can also give some base definitions according to which we can sort of. It's just for a matter of convenience in order to identify categories. So a spectrum is called connective if it doesn't have any negative homotopy. So it only has the homotopy is considered only on the positive side. And so it's denoted by this upper index Cn. And we say a spectrum is n truncated if it vanishes after n. So it has only values till n. After n, it's all just identity. It's all just a trivial object. And so combining these two, we have this notion of a discrete spectrum, which is like it's a zero connective spectrum in some sense. So if pi n vanishes for every n not equal to 0, then we say it's a discrete. So in particular, this is a very strong idea that sort of led to this idea of building this SpDM that we want to sort of classify. Given any ring, we can see this ring as an infinity ring with the discrete spectrum. So this ring doesn't have like a priori any ring doesn't have any commutative ring doesn't have a higher homotopy data. So you can sort of see this as a discrete spectrum, and then you can travel between these two worlds. So whenever we are coming back to the normal categorical sense, we have this notation of Hart. So spectra of Hart, it just means the discrete. So it is just a spectra where the rings are just discrete, right? So which says that there are spectra which have rings that are not discrete, and that's the world of E infinity rings. And there is this one important structure that this spectra comes with, which is the smash product. So the smash product is a unique functor such that it preserves colimits in each variable, such that the smash product retrieves back the space itself. And with this smash product, the category of spectra becomes a symmetric monoidal infinity category. And then this thing is seen to be commutative, unital, and associative up to coherent homotopy. So we're not going to define what a coherent homotopy is, but you just have to take it on faith from me that coherent homotopy is sort of a homotopy notion for infinity categories. Right. So finally, we can define what an infinity ring spectra is. So given any symmetric monoidal infinity category, then you just take the commutative algebra objects on C, equipped with this obvious multiplication from the smash product, and these objects, they form a subcategory of the whole spectra, and they are called the E infinity ring spectra, right? And these form infinity categories in a natural sense. And then, so for example, a sphere spectrum is an example of an E infinity category because we have this smash product, natural smash product from the topological spaces. So this makes this category into a symmetric monoidal category. And so one can verify that this is sort of commutative, monoidal and associative up to coherent homotopy. Yeah. And then, so this covers one part of the world, and the other part of the world is sort of called the stacky world. So where you have this generalization of one category into a two category, and then Deligne-Mumford stack sort of like is a very important object of study in this setting. So very roughly, a stack is called a two sheaf. So it has a because a sheaf usually takes a data on a set. So it takes values on a set. And if it takes value on another category itself, then it's called a stack. So is there any questions? Okay, perfect. So why do people study moduli theory? So I'm not going to give a full detailed explanation of it, but just to have a glimpse so as to understand why we are doing all this in the seminar. So moduli theory is a very strong theory that emerged from this question. So can we classify isomorphism classes of mathematical objects of a given type? So this is a very natural question. So we can sort of ask this question in a very flavored and different way so as to get good outcomes out of it. And this is one diagram that sort of unifies the whole idea of why do we consider the stack theory and why is it different from the normal set theory that we have. So I'm not going to dwell much on this one, but so if you want to see a very good introduction, I highly suggest this notes. Like it's still a draft. It's by Gerard Alper, and it's notes on stacks and moduli. It's on his webpage. Gives a very smooth introduction to moduli theory. So a particular moduli space is a space whose points, just the points of the space, are in natural bijection with isomorphism classes of whatever object that we need to study, right? So for example, so you take the plane R2, and then all the lines to the origin is already classified by this guy called the projective line. So a point on the projective line is exactly same as a line through the origin. So sort of like this is a very interesting and different perspective of seeing. So we know how RP1 is defined, but seeing RP1 in this way gives a very sort of exciting way of looking at how mathematical objects can be used to exploit other areas in mathematics, right? So and then there is this example of unlabeled triangles. So a triangle is unlabeled if sort of like so each vertex are different and each of the sides has a different kind of length. So one can also ask this question of can you sort of classify all this unlabeled triangles? And the answer is yes. So it is given exactly by this space here in R6. So we see like in these two examples, there is a very strong positive answer in a sense that we can say, okay, if you have the problem, so if you have this as a problem, okay, just we have this as a solution. So there is like a direct match and approach. But unfortunately, this is not the case for many of the interesting objects that we need to study. So for example, people try to study this smooth curves of genus G. This is a very classical geometrical object. So we cannot have a single space that sort of gives the data about this classifying problem. So in other words, people call this a moduli space problem. Also called the fine moduli space problem. So for example, RP1 is a fine moduli space of this problem, but you see that this does not admit a fine moduli space problem. So the idea is to not look for a space, but look for something more extensive so as to sort of include the abstraction that sort of inhibits having this fine property. So in other words, fine moduli space don't work because there is a very high notion of automorphism. So these spaces carry these are very symmetric in some sense, and they carry a pretty much data of automorphism with them. So it sort of inhibits them to have a very good representative. So the idea is to build a family of spaces, not just a single space, but a family of space. And you just build it with the desired property. So in other words, you don't need moduli space, but you need what you need is a moduli stack, right? So this is just a diagram that depicts it. So you have something. So you have like a base category, and then you build another category which forms as a sort of a. It looks like a vector bundle construction in some sense, but except that in vector bundle at each point we have a fiber which is a vector space, but here at each point we have a family which can also be like a unique object itself. For example, for each point in S, you can just have a curve on it. So you have, so in other words, this family parametrizes all the curves that you want to study. And so this is a very natural notion of what people call a pre-stack. So pre-stack is this following data. So if this is the space X and this is the base space, we have this map X to S here, and then it's called a pre-stack if for every diagram we have a pullback, and this pullback is universal. So it's a very unique morphism, making this diagram a pullback diagram. So basic example is any pre-sheaf is a pre-stack, for example. So in its very basic sense. And so a pre-stack can become a stack if it sort of satisfies more specific gluing criteria, which is called which is like a morphism should glue in a very nice way and the object should glue in a very nice way. So if you just go back to the definition of scheme, you can sort of see that these are very, very sort of, these go in line with the definition of a pre-sheaf and a sheaf. So in other words, any sheaf is also a stack. So this is just a two categorical generalization of what a stack is, right? And then so people sort of study these kind of inclusions for each of their representative senses. So in this talk, we'll just define what a DM stack is. So this is a very stacky way of defining it, but in our talk, we'll adopt a very infinity categorical language of adopting this, right? And then, yeah, this is something about gluing data that we'll also see in the talk. A scheme is an affine scheme, but glued with a Zariski topology, and a Deligne-Mumford stack is an affine scheme, but it's glued with a spectral topology. So, and then one important definition that paves a very good role for DM stack is notion of Henselian ring. So a local ring is said to be Henselian if it satisfies Hensel's lemma. For example, so there's this quotient map from this space to its quotient. So if you have a object here and then you take the image under this quotient map, and if this has a decomposition here, so can we sort of lift this decomposition to a decomposition of F here? So if we can sort of do this, then those rings are called Hensel ring. So basic example, so any field is a Hensel ring, and a complete host of local rings and the p-adic integers are also a Hensel ring. So it's sort of like a very basic object to study. And so we say a ring is strictly Henselian if the residue field is a separably closed field. Okay, perfect. Okay, so what are the end goals of this talk is, 1 second. Okay, so we have to make sense of this infinity category, which is called the spectral Deligne-Mumford stacks, right? And you have to build the notion of quasi-coherent sheaves on this kind of category. And then as a important theme, we have to sort of restate the Tannaka duality in algebrogeometric sense that sort of finds place in this category that we are about to construct, right? So if there is one sort of slogan that I would like to I would like you to keep in mind is, so you sort of locally model what we want to have, and you have to globally glue them with the knowledge of what you need to represent. So depending upon what your needs are, you sort of build it locally and sort of glue it globally using some kind of constraints. So manifold is something that is locally a Euclidean space. So we just glue it from Euclidean spaces. That is fine. And then a bit of generalization is a scheme. So schemes are sort of locally spectrum of a ring. That is fine. So from here, you can sort of divide into two families. So there's this notion of spectral schemes and this notion of DM stacks. And we are going to see what does this local thing stands for in this category. And then these description will sort of give us a description of what a local SpDM should be naturally, right? And then I'm not going to dwell on this because in the previous talk, Matthew already told us about what a algebraic variety is and also what a scheme is. So in particular, scheme is a topological space with a sheaf of rings. And then in other words, it's a ringed space that has a very sort of that has a very particular gluing property such that locally it's patched by affine spaces. So once we have this category of schemes, then we can talk about a spectrum associated to a ring, right? So because spectrum of a ring sort of gives us a affine scheme, and they would be like the first example that people see in scheme theory. Okay. So this is just about how to put a topology on a given scheme. And then so once we have this topology, then we can build something called as a structure sheaf with respect to this topological space, which sort of records the regular functions defined on this space X. Right. So I'm not going to define this whole thing, but it sort of crisply says that at each point you should be able to find a neighborhood in which it is represented by a rational polynomial like R by F, which are both polynomials. And then affine scheme is something that is isomorphic to a spectrum of a ring itself. So we use this mod spec of R notation to denote the underlying topological space, because spec of R would also mean like the spectrum of a infinity ring, as we would see in the top, right? And then so now moving to the important part, it's the first part of the talk, which is like what are spectral schemes. So what we are going to do in this first part is like, so we're going to replace the sheaf of ordinary commutative rings by the sheaf of E infinity ring that we have just described. So we are not going to touch the topological space. It's going to be the topological space till the end, but we're going to just make the construction on the ring part. And then you're going to define the spectral schemes via quasi-coherence, some quasi-coherent conditions on OX. So by OX, I don't mean the usual, the one categorical structure sheaf, but like the infinity categorical sense. And then, of course, one should have a very basic example in the series so as to have a good idea of what we are doing, right? So that would be the affine spectral scheme. And quite shortly, we'll also see how to sort of characterize them using this local data. Okay, so a spectral scheme is a heuristic to keep in mind is a spectral scheme is a topological space with a notion of homotopies on the structure sheaf setting. Okay, so what is a spectral scheme? So we've seen that sheaf can take values in set, but it can also take values in any category, in particular any infinity category. So we have this notion of pre-sheaved valued in this category C, which is this contravariant functor here. So it goes from, if you have an object X, which is a topological space, and then you can sort of define this pre-sheaf given by the open sets. So for example, it would be something like, a home into that open set. It could be one of the example of pre-sheaf, right? And so a pre-sheaf is a sheaf if it satisfies the obvious descent criteria. So sort of have to, so if one could make a statement globally by just looking at how it behaves locally, then we say that a pre-sheaf becomes a sheaf. Right? And so to define a spectral scheme, we have to know what a spectral ringed space is. This is just exactly the analogy between how we do scheme theory. So a spectrally ringed space is exactly the pair O and X and OX, where X is the topological space, clear? And OX is just E infinity value sheaf. So we are not just taking commutative rings, but also the values in E infinity rings. So this is just the notation we use to denote the spectrally ringed spaces, which is top C-alg. So C-alg means commutative algebra objects, so in short, right? And then, so in schemes, we don't have a homotopy structure imposed on it. So this we don't see with, so naturally in any scheme theory book, you don't see a definition of homotopy structure imposed on that because the ring itself is discrete, there is no homotopy data. But a spectrally ringed space, as we've seen, so since we have equipped it with E infinity structure, we have a homotopy, like non-trivial homotopy structure living on it. And then, so how do we define that? It's a very natural definition. So you have a topological space and you have a sheaf taking values in spectra. So we have defined what a spectra is. And an infinity ring is a full subcategory of spectra spanned by this very nice objects which are commutative. So once we have this sheaf, then build this pre-sheaf by sending any open set to this pi n of f of u. So for example, f of u takes value in spectra, and we have seen how to sort of compute homotopy groups of spectrum. So just use that spectral computation to have this nth homotopy sheaf, which is just the sheafification of this pre-sheaf, right? And then the one nice structure that this carries is like if you have a sheaf of infinity rings, then the pi 0 of OX is the sheaf of ordinary rings. So I mentioned that the X comma OX, like the OX is not the usual structure sheaf, but it's an infinity version. But just taking the pi 0 component, you just go back to the spectral, like we just go back to the scheme theory world. Right, so you have this base pi 0 of OX, and each of this higher homotopy, it sort of sits as a module. So you can consider this as a base ring, and this is a module over this ring. So this structure is very useful to sort of talk about coherent sheaves on this space, for example, as we'll see. So we say that spectral schemes encompass schemes. It exactly means that there is a functor from the category of spectrally ringed spaces to the category of ringed spaces, which is given by just forgetting the higher homotopy. So you just have OX, which is an E infinity ring, so it carries homotopy. It's just taking the pi 0 component, just forgets everything. So just get the plain plain structure sheaf, and so in this way we can see this as an extension of scheme theory. So this category retrieves back the category of usual ringed spaces. Okay. So now we can finally define what a spectral scheme is. A spectral scheme is a pair X comma OX such that the following occurs. So first of all, a spectral scheme should sort of extend the scheme, right? So if you just take the underlying object, it is a scheme. So this is something that we should make sure, because we are going to build things out of this. And for every n non-negative, this guy pi n of OX is a module over this ring. And this is actually a quasi-coherent sheaf. It's not just a module, it's not just a sheaf, but it's also quasi-coherent. And locally, there is a condition on this. So for every open set U, if you sort of restrict this sheaf, then it has to be an affine scheme, like one categorical affine scheme. And there is the canonical map between taking pi n of a sheaf and taking pi nth sheaf. They have to be somehow the same. Like it has to be isomorphic up to some coherent data. And then finally, each of the pi n's should vanish for n less than 0. So there is this. I mean, so this 4 is sort of like a variant, I would say. So because Lurie defines a spectral scheme to be something that satisfies all these 4 properties, but he also mentions that people consider spectral schemes satisfying only this. So in particular, there's a theory of non-connective spectral schemes. But for our talk, we can just consider all these 4 to be these conditions to be sufficient for a spectral scheme, right? So once we have a definition, it's good to know a very basic object, right? So we have to construct a basic object of a spectral scheme. So we have in the scheme theory, the basic object is an affine scheme. So in a spectral scheme theory, the basic object should be an affine spectral scheme. So it's just a paraphrasing, but you will see it is also mathematically coherent. So how do we do that? So a spectral scheme is this topological space and sheaf of E infinity rings, right? So we can talk about the spectrum of this ring, just like how we talk about spectrum of any ring. And in this sense, we will mean like a spectrum of a ring spectrum. So somehow it is sort of defined by an universal property of having localizations, right? So just to fix some notations, if A is a E infinity ring with the underlying commutative ring to be R, we take the pi 0 of A. So you say an open set is affine if it is open, if it is if it is open with respect to the usual ring, like the commutative ring, like the underlying ring structure. And then, so just as we have the notion of localization of a ring, we can also talk about localization of E-infinity rings. So if you have an E-infinity ring, you take an object from the underlying ring, and then you can invert this object. And then, so the definition is exactly what one should expect, right? So localization has a universal property, and then, so this is like an infinity categorical universal property of what a localization should obey. So just inverted and maps into any other ring should be uniquely given by the map spanned by these maps taking elements to an invertible element in B. So if we sort of go through this definition, it exactly parallels that of a localization of a very normal ring. Right. And then now we can define what a structure sheaf is using this data of localization. So if you have an E-infinity ring with an underlying ring R, then also with this data of sheaf and a morphism of sheaves, then we say that a sheaf is a structure sheaf if it obeys these three properties. So for example, for every element X, there should be this. So this is like a principal open subsets in this theory, which is just all those primes that are not contained in this that are elements that are not contained in this primes. So for example, the composite, it will induce a map, induce an equivalence of E-infinity rings. So, and then one also needs this map, this canonical map to induce an isomorphism on the underlying ring structure. So yeah, depending upon the variant we need, we could sort of consider the non-connective spectral scheme or a connective spectral scheme, but the construction is the same and essentially gives you what is called the structure sheaf of the underlying scheme, right? So we denote this pair by this notation here, and this is called the affine spectral scheme of a given E-infinity ring, let's say. All right. So as I've mentioned before, any commutative ring can be seen as a discrete E-infinity ring. So there is a path between the world of schemes and spectral schemes, but sort of it's not very clear how to go and come back, because any commutative ring can be seen as a discrete thing. But when you have a E-infinity ring, how do you see? If you just take the pi0 component, you just forget all of the structure, sort of like you lose the homotopy. So it's not a very nice path to come back. To go, it's fine, but to come back, it's not a very valuable path. But nevertheless, we have this good criterion, which is like just take the pi0 of this structure sheaf. It is exactly isomorphic to the structure sheaf itself. So this isomorphism is not a strict isomorphism, but it is an isomorphism up to some coherent data. And if you just to get back the original sheaf, you just have to sheafify the underlying structure sheaf. That's enough. And one can also ask this question locally. So locally, also we can sort of have an isomorphism up to some coherent data. Right? So finally, we can talk about this category of spectral schemes, which is just this pair of spectrally ringed spaces X and pi0 of X, which satisfies like a criteria very similar to a scheme, how a scheme satisfies. Right? So a spectral scheme is called local because a scheme is a locally ringed space, so it has a notion of local ring. So a spectral scheme also has a notion of a local ring, which is like defined in exactly the same way. So it is a locally spectrally ringed if you just take the underlying ring. If it's a locally ringed space, then we say that the spectral scheme is itself a ringed space. And this is just a matter of notation. So we define this category of spectral schemes by this SPSCH, and NC means a non-connective part. So depending upon the flavor we need, we can sort of take the connective or non-connective theory. So, and yeah, the objects are exactly this pair, and the morphisms are. So it's exactly defined how a morphism between a scheme is defined, except that the topological part is fine, but except that it's not a morphism of commutative rings, but it's a morphism of E-infinity rings. And this has to be a local homomorphism as well. So it has to obey the local ring structure, right? So just to conclude this part with, so we'll see that affine schemes have a very unique property, in a sense that if you have a affine scheme, then taking the global section functor, which is like you take the global section of this with respect to the structure sheaf, then get back the ring itself. So if X is spec R, you just retrieve back the ring itself. So this happens if and only if the scheme is affine. So we see that it is also true for spectrally affine schemes, right? So if you have a locally ringed space, and if A is an E infinity ring, and then this is the spectrum defined in this way, then the composition with the canonical element, so A is like the base ring, and then mod of this is the underlying topological space, and O of this means the structure sheaf with respect to the E infinity structure, right? So this induces an homotopy equivalence. So here we would have an isomorphism of rings, but here it's just an homotopy equivalence. So there is like an homotopy data that comes into play here. So in fact, one can already characterize affine schemes by just this property. So if you have a spectral scheme is affine, if and only if the underlying scheme is affine. And so in particular, a spectral scheme, a locally spectrally ringed space is affine, if and only if for every open cover, just restrict it, and if it is already affine, then the original space is also affine, right? So I'd like to take a pause here and then continue back. All right. So we have seen one part of the world where we have modified the ring structure. So the second part of the world is the Deligne-Mumford stack, where we are going to replace the topological space by a higher version. So in other words, a Deligne-Mumford stack differs from a usual scheme in two different ways. So the first way is like a scheme as a topological space, but this one as a space, it's a Grothendieck topos. It's a higher version of a topological space. And then locally, a scheme resembles a spectrum of a Zariski topology, but a DM stack locally looks like a spectrum of an E infinity ring, but with an étale topology on it. Right. So just to give a brief introduction on what happens in the world of topos theory. So a topos is, heuristically speaking, it's exactly like a category of sets, but there's some additional data which pertains to having localization properties among the objects in the category. So a category C is called a Grothendieck topos. So there are several equivalent definitions, but I just picked up the one which is more convenient to put up in this frame. So a C is Grothendieck topos if there exists a small category D, and an inclusion of C into the pre-sheaf category of D. So in other words, and of course this inclusion has to preserve limits. And in other words, a Grothendieck topos can be like loosely considered as a category of sheaves on a Grothendieck site. So for example, so we have the category of motivic K-spaces. So it is built by objects which are sheaves in Nishnevich topology on the category of schemes. So these are like very much studied objects to sort of relate the world, like work in the algebraic geometric setting. Okay, so then we can talk about what are local rings in a topos. So in particular, a ringed topos is just a pair of X with OX, such that X is a Grothendieck topos and OX is a commutative ring object of X. So in particular, we are not going to change the ring structure. It's going to be like a very basic ring that we all know, but then we're going to equip this guy with the structure of a topos. So this extends naturally to a category, which is, I'm not going to spell it out, but we're going to denote that by this notation here. So whose objects are just pairs satisfying this natural property like this. So it is just a pair of a topos and a commutative ring, such that on the topos part it is a geometric morphism between topos, and on the commutative ring part it is exactly like how a map of rings in scheme is defined. So, and having two topos, we can talk about a map between these two topos, which is given by this diagram which has to commute, right? So as a first example, so so we've seen that topos is a generalization of like a topological space, right? So in particular, topological spaces should be an example of topos, and that's what exactly we are going to see. So if you have a topological space and you have a structure sheaf, which is just a sheaf of commutative rings, then one can see this OX. One can see this topological space as a topos built on the category of sheaf. So assigned to an topological space, there's a very natural topos, which is the sheaf taking values in set. So it's called set value sheaves on X. So this pair would be a very first example of what a ringed topos would be. And so locally a scheme was affine, right? So what is a topos locally? What does it look like? So what are local objects in this theory? So a ring is called local. We know it has a unique maximal ideal. And so if you have a topos, what does it mean to have a local ring structure in topos? So you have a topos with a final object 1 and OB its commutative ring objects. Then attached to a commutative ring, we have a group which is just obtained by taking the group of just take the group with respect to the multiplicative structure. So it's a group of units, in other words. So we say that so this is defined by a pullback diagram here, so which we are all familiar of from the algebraic group structure. And we say this sheaf is local if the following holds. So this structure sheaf has to be locally non-trivial. In other words, the map from the final object to the sheaf has to be a trivial morphism. Yeah, so it's given by the zero, it's otherwise called the zero section, and the fiber product is an initial object in this category. And then there is this criterion which sort of resembles how one can translate the notion of local ring from the normal ring structure, right? Okay, and then if you have two topos, like you have two rings in topos, so we can talk about when a map is local. So this is about an object being local, and this is about a map being local. So and it's obviously defined by this pullback diagram. So we say that this map between O and O tilde, these two topos are is local if the corresponding map is a pullback in X. Right, and so we have this. So we see that this is not just a one category, but also there's a data of homotopy between maps. So in particular, it's a 2 category, and we denote that by this super index LOC, which is like local objects of this setting. So once you have local objects, now the idea is to try to sort of glue it, right? So how are we going to glue it, and what are the affine kind of objects in the setting? So these are the next natural questions. So we have a ringed space, and we say the structure sheaf is local if and only if if it is local when considered as a commutative ring, like a very base ring. If it's already local, then this OX is defined to be local as well, and it's an if and only if condition. Okay. So we have seen that Deligne-Mumford stack is something that is locally spectrum of an étale topology. So quickly, we're going to see how is the spectrum constructed in this case. So first of all, why do we need to consider étale spectrum? So why is Zariski not enough and we have to go to étale? That's because a very short answer is we would want this topos to have a strictly Henselian ring structure, because we'll see that the Deligne-Mumford stack have this strictly Henselian ring structure that sort of makes it into a 2-1 category. So it's not just a 2 category, but also category in which like 2 morphisms are invertible. So this is a more added structure, and that happens only if we have the étale topology. We need to have more finer covers to sort of have this Hensel lemma work. So the remedy is to replace Zariski by étale, and an étale topos is something that looks locally like étale R algebra, I would say. So given a ring R, just denote this category. So remember, hard is like whenever we see hard, it like also in the next talk, it means that we are just taking the one categorical object corresponding to this thing. So C algebra R would be like the commutative algebra object, but like the ring objects. Okay, there exists a full subcategory which are generated by et al. R algebras. So one can equip this with the Grothendieck topology, which are so for a Grothendieck topology, it's enough to give a covering map. So in particular, we just take the finite maps, so finite indices and maps which are of this form, such that A to A alpha as it acts as a covering sieve for this topology, which we'll call et al. Topology, and this map has to be a faithfully flat map. So one of the equivalent definitions of being an et al. Topology, right? So we call this sheaf taking values in set of this object here to be the et al. Topos attached to this ring R, and this is exactly the functor category from this category to the category of sets, right? And this is exactly generated, or in other words, spanned by those sheaves which are et al. With respect to this covering defined here. Okay. So once we have defined this local notion, then the idea is to sort of form a basic example of this theory. And the basic example is like obtained by saying what a structure sheaf is. So because every other example has to locally look like this, so it's better to have a structure sheaf defined in the first place, right? So so you have a sheaf defined in this way, so which sort of forgets the R et al. R algebra structure. So you have an et al. R algebra, and then you sort of forget it, and you get the basic underlying ring. So this can be sort of shown to be a sheaf in the et al. Topology. So the ring to topos, which has this as its structure sheaf, will be called spec of R, which is the basic object of study in the topos theory. So it's et al. Spectrum of a given commutative ring. So now we have this, how to develop a topoi version of DM stack. So in the beginning, we have seen a definition of DM stack using the description from the moduli theory world. But in this setting, Lurie gives a definition of DM stack using like the infinity topoi version, right? So we're going to model this DM stack using this locality property that it has to locally look like it has spectrum of some commutative ring. So in particular, a ring to topos is a Deligne-Mumford stack if there exists a collection U alpha in X satisfying these two conditions here. So briefly, this means that they have to cover, it has to be a covering set first of all, and then the natural map to the final object has to be a surjection. It has to be an epimorphism. So for each index, the ring to topos is equivalent to the ring to topos of SpectR algebra. So this is some local criterion that we wish to have in this category. So we're going to denote this by DM. It's a ring to topo. It's a category of ring to topoi generated by the DM, generated by the stacks that sort of satisfy these two properties. And locally, we have something which is called affine DM stack. So a stack is affine if it is equal to spec of R for some ring R. So we see there's a very close parallel connection between scheme theory and spectral scheme theory and Deligne-Mumford stacks, and we are going to soon connect this to a point. Okay, and why do we need to study affine objects again? Here is that affine objects sort of generate the whole DM stack. So everything about that stack is already encoded locally into the affine objects of the DM of this category. So in particular, so a given ring to topos is a DM stack if and only for every X there is an effective epimorphism from this coproduct to this X, and such that each of this restriction to the open subsets is actually an affine object. So further good to know is something that, and ring to topos is DM, that already implies that locally it's DM for any, it's not just affine opens, but any opens. Any opens. And then if X as a covering using some open subsets such that restricted to the open coverings, if it's a DM stack, then it lifts to a DM stack in a global structure. And the collection of affine objects is closed under fiber product. So this is also something that would be very useful to sort of make many constructions. So to this end, we sort of define the two category of DM, Deligne-Mumford stacks, which is in fact a 2-1 category. It's not just two category. And this follows from a more general fact, such that if whenever you have a two ring topoi, and then OX is strictly Henselian, and this one is a Deligne-Mumford stack, then this category that we have defined before is actually a groupoid. So you can see that every morphism is invertible, and in particular, having a strictly Henselian structure on one of that would sort of imply that the category itself is like 2-1 category. And one of the important notion is talking about quasi-coherent sheaves in this category. So this is very useful to connect this world of infinity topos to the infinity sheaf world, sheaf taking values in infinity rings, I mean. So given a DM stack, so you can talk about OX module objects. So these are exactly the module that we would think in a normal ring. It behaves exactly like the same way. We'll see it now. So and then for attached to this each X, we have this structure sheaf, which is given by this home set here. And this is in fact a commutative ring. And then one can define. So this is for the structure sheaf. For any given sheaf, one can define this to be the home taking values in F, the sheaf F. So we say such a sheaf is quasi-coherent if it satisfies this criteria here. And this exactly translates from the criteria from the scheme theory. So for every morphism U to V between affine objects, the induced map between the corresponding structure sheaves defined on them has to be an isomorphism of modules over the commutative ring. So it's a very sort of natural condition to have. And characterization, how can one just characterize quasi-coherent sheaves using module structure? So there is this good correlation between category of quasi-coherent sheaves on the SpEch A and the category of discrete A modules. So in particular, if we have a sheaf, it is quasi-coherent if and only if there's a discrete A module. So by discrete, I mean this module doesn't have a homotopy structure. So all the pi n's for n not equal to 0 are just 0. And for which F is defined as this tensor product here. So this would be sort of a derived version of a normal tensor product called the derived tensor product. And conversely, any discrete A module, so there is this theory of faithfully flat descent. Using this descent, one can see any discrete A module to have this derived product here, and this is actually a sheaf with respect to the étale topology. So sort of having a discrete A module already sort of gives a good amount of data about quasi-coherent sheaves on SpEch A, in particular on DM stacks as well. So we have developed these two notions of infinity topoi and sheaves taking value in infinity rings, but how can one travel between these two worlds? So the idea is to sort of set up this object, which is a pair of infinity topos, and not just commutative rings, but taking sheets of infinity rings like defined on the topos X. So this is sort of the bridging construction that sort of glues these two worlds. So given any infinity category, so there's a natural way of associating a sheaf to it, which is just given by the open subsets. Right? So instead of any category, we can also build a sheaf on infinity topoi, which is just some sheaf that takes values on a given topoi. So for example, a pre-sheaf here becomes the sheaf if and only if it satisfies this canonical map criteria. So this has to be an equivalence of category. So exactly the same as we have seen in the one categorical setting. So basic example is if you have any topological space, we have seen that. So this topological space is considered as infinity topos by taking the sheaf object on it, defined on the set. So instead of set, we can also take values on any infinity category, which is like denoted here. And then this is exactly the sheaf taking values in C, but defined on the open subsets of X, so which we use the notation U of X. So this is like a partially ordered set category where the objects are just opens of a given scheme or an object X, and the morphism is what it intuitively should be. So more specifically, we are interested in replacing this this topology by any infinity category of spaces. So spaces meaning can be topological spaces, simplicial sets, abelian groups, anything. and then so we can sort of have a same description of sheaves on this in category of infinity spaces. And one more important thing that we would like to have is this to have a very nice property. So in a sense that if you have an infinity topos X with any arbitrary infinity category, a C-valued sheaf on this is a functor. It's a contravariant functor given in this form. So it actually preserves limits. So in particular, we see that if this C that we take is a presentable infinity category, so meaning that a presentable infinity category is something, so vaguely put, is a category that can be sort of formed by just having co-limits. So if you know the notion of co-limit in a category, and if you can build any object just using some, just by using the spans of these co-limits, then that category is supposed to be a presentable category. So we see that if C is presentable, then the sheaves taking values in C defined on any ring topos is also a presentable category. So this is a very nice notion. So in particular, we'll see that any quasi-coherent sheaf is also presentable at the end of this this slide. So instead of taking any random category, so we can just take C to be the category of spectra. So we know what a category of spectra is, and yeah, so the natural way of talking about E infinity object is to talk about category of spectra and restrict that to the commutative objects, which are exactly infinity rings. So having C to be spectra, we just define the category of sheaves on infinity topos, taking values in spectra. This sort of connects these two worlds, and this is defined using the following version. So there is a forgetful functor that runs between commutative algebra objects taking values in spectra, and you just forget that it's commutative, and then take the spectral object, the underlying spectral object. So this forgetful functor, it preserves small limits, and if you are given any infinity topos, there's a canonical equivalence of infinity categories, which is just sort of like, it's something like moving brackets, moving between brackets, as they would call in category theory. So this has to sort of hold. This actually holds when the infinity category is a category of spectra, because it preserves small limits. So given a sheaf of infinity rings, then so we can talk about the notion of homotopy groups on this by just composing the structure sheaf with this forgetful functor, right? So this would, for example, give us a pi naught of a given infinity ring. So in order to take pi n, we need to sort of have this functor, which is called the shift functor. Sort of like if a spectrum is En, this sort of shift functor, what Em, and the shift functor sort of shifts this to Em plus n. So sort of it shifts the indices, for example. And using the shift functor, one can sort of define what is called the nth homotopy sheaf associated to this ring topos. So, and this would be like the very basic setup that we would need for the next talks. And yeah, so as we have seen in the spectral scheme case, so pi naught of this sheaf is actually a commutative ring object, like it's a one category, and then pi n of this one actually it sits as a module over this category here. So just the same definitions as in the one categorical case, as in the spectral scheme case, which is a sheaf is connective if the pi n that we have defined just now, if it is 0 for every n less than 0, and it's n truncated if it sort of vanishes for all k greater than n, and it's discrete if it is 0 truncated, meaning that except 0, everything except n is equal to 0, pi n's all vanishes, right? So one underlying theme is so the connective objects which are n truncated in the category of spectra, in the category of E infinity ring spectra, is exactly equal to the infinity category of commutative algebra objects with respect to this spectra. So in a sense that we have a good description of E infinity rings using the connective spectral schemes. And for example, just taking n is equal to 1, you just retrieve back the one categorical description of a commutative ring. So finally, we can now start describing what is the main object of our study is. All right. So far we have seen two different generalizations. So one is like we have seen what is a spectral scheme, and we have seen what is a DM stack. So the idea is like a spectral scheme is sort of a left-derived version of a scheme, and the DM stack is like a right-derived version. So what I mean is like so you have this natural inclusion of scheme into this spectral schemes. They don't preserve limits. So in other words, you just take three schemes and sort of like you have maps over Y, and then you have this map, and then you take the one categorical pullback, and then see it as an infinity categorical pullback. So one can do this, and then this would actually be it would actually be a limit pullback in terms of infinity categories, but it doesn't sort of reflect the same thing in one categorical sense. So this doesn't happen. So in other words, it means that this sheaf that is attached to this Z, it need not be zero truncated. So it means that precisely means it can have higher homotopies. So we are sort of killing the homotopy by taking the pi zero. So this is not a bug. Actually, it's a feature of spectral schemes. So in the same way, if we take the inclusion of schemes into DM, it does not preserve colimit, so limits and colimits. And then, for example, colimits are obtained by taking quotients. So if you have a finite group acting on X, so one can talk about scheme theoretical quotient and stack theoretical quotient. So in particular, we can obtain this by taking the coarse moduli space of this space here, but then you can't get this space back by if you just know the space. So there's a mismatch of data. This happens if and only if the action is free. So it's not a very sort of prevalent notion. So again, it's not a bug, but it's also a feature that helps us to know more about the object, right? So just to define this SpDM, so a spectrally ringed infinity topoi is just this pair where X is an infinity topos and O is like sheaf of E infinity rings. So we have now come to the setting where both of these indices are advanced structures somehow. So it just denotes this category by this notion here, and the objects and morphisms are exactly how one should expect. So it's just it just include the morphisms and definitions by from both the theories, and naturally it sets a base here. So for any infinity topos X, so still denote the underlying topos by this notation, and then one can talk about homotopy groups also in the setting. And the homotopy 2 category of this one, it can be sent to a 2 category of this by just taking the heart of this. So they just take the underlying object. So it just go back to the 2 category from the infinity category. And then, so we have seen what et al spectrum of a normal ring is, but one can also define et al spectrum for an E infinity ring. And then it's exactly defined using the data of being strictly Henselian, right? So if you have an infinity topos, then you have a sheaf of infinity rings on X. So we say that OX is local if first of all the pi zero component is local, and then if OX is said to be strictly Henselian if the pi zero is Henselian. So this we can see as a parallel setup how we define DM stacks. And then a morphism is local as exactly what we expect it to be. So in this setting, we have a global section functor, just like we have in scheme and spectral schemes. So global section functor is just it admits a right adjoint, which is just forgetting the. All right, so okay, so you just have a topos, and then you take the global section with respect to the topos, and this is the structure sheaf of an infinity ring that we have defined. And then, so for any infinity ring, there exists a strictly Henselian spectrally ringed infinity topos and a map given in this way. So plus some universal property that we are not going to see. So for example, having a strictly Henselian thing is very important, as we have seen it in the DM stack world. And then if you have an infinity ring and a structure sheaf, so you can have so attached to this, we have seen there's a forgetful functor which forgets the R et al algebra structure. And then we have seen it's a sheaf with spectral topology. And in particular, it's also strictly Henselian, so which is the desired property that we need. So in particular, it retrieves back the ring that we started with. So this acts as a spectrum. This acts as an affine kind of SpDM in this setting. So this pair is what we call the et al spectrum of a given ring R. So here R is a infinity ring. So just remember. So now we can introduce what finally the object that we are trying to seek, right? So a spectrally ringed infinity topos is called a non-connective. So this it's a variant. It's a spectral Deligne-Mumford stack. If you have a collection satisfying this criteria here. So again, like just tracing it from the beginning. So the idea is to like define what we need locally and sort of like use it to globally patch the data we need to achieve, right? And a spectral DM stack is a non-connective spectral DM stack, but the sheaf is actually connective. So it's just a variant, as I've mentioned already. So as a basic example, given any infinity sheaf, you can say it's connective. Taking a connective infinity sheaf, then taking the spet of it, like taking the étale spectrum of it, we get what is called the affine guys in the setup, let's say. So it's a very basic example, and we'll see any spectral Deligne-Mumford stack locally looks like this. So it's sort of patched from the affine, which is defined with respect to this étale topology. Okay. And right, so finally we have the notion of quasi-coherent sheaves in spectral algebraic geometry. So given any spectral Deligne-Mumford stack, one can associate a stable infinity category called the quasi-coherent sheaves on X, and it is defined by this data here. So first of all, we've seen that there is a notion of module over OX. So whenever we have a notion of module, we can build a sheaves with sheaves taking the values in this module. And then exactly how one defines in scheme theory, you can say when a sheaf of module becomes a coherent sheaf. So in this setting, we say that so there's a full subcategory called QCO of X, which is called the infinity category of quasi-coherent sheaves, and it is defined by this sort of patching data here. So for every morphism from U to V, the restriction is quasi-coherent on this one, and so being quasi-coherent here already means quasi-coherent here. So it's sort of like pulling back properties between maps. And conversely, we are given an effective morphism into V, and each restriction, if it's a quasi-coherent sheaf, then the whole global object should already be quasi-coherent. So why do we need to study quasi-coherence? Is like that's this nice property that if you have, so for affine guys at least, the global section functor admits a fully faithful left adjoint such that the essential image is exactly the quasi-coherent sheaf. So in a sense, they sort of represent the category in a very nice way. And if you have a connective SpDM, then you can see the infinity category. First of all, so the infinity category of quasi-coherent sheaves is actually closed under small colimits, and it's also a stable infinity category, which is very, very useful. And it is also presentable, meaning that just using the small colimits, you can sort of retrieve back the whole category itself, right? And of course, like the structure sheaf that we have defined is contained in the QCO. So it means that it sort of gives the notion of unit objects in this setting, and also like it is stable under the derived tensor product, which means that this whole category can be seen as a symmetric monadal stable infinity category. So remember that also this category of spectra was once this example. So this is the second example of a stable infinity category, which has this symmetric monadal structure. So just to finish things off, just to connect this whole idea with what we are going to see in the next talks, is the Tannaka reconstruction. So given a scheme X, this is a very basic question of you take the global section functor that we have seen, and we can ask if we know something about this ring functor, can we say something about the scheme itself? This is a very, very basic but very profound question. So put precisely, what it means is like, so this is just the number from the SAG. You can just verify if you want. So if you have a commutative ring and every map, so this map is also called the X of A. So it takes like it takes the rational points on a given scheme X somehow. So this map already determines a pullback from this global section to A. So in other words, we have this map from the this is from the rational points of X with respect to A this home of this category here, of taking these values in this category. So in particular maps of this form, right? So this is defined by sending an f to its pullback. So we can ask, when is this map a bijection? This is like the first school of thought. And the second school of thought is like, you can ask, if we know, like, we don't care about the bijection, but can we categorize these functors for which this is actually an equivalence? So can we have an object that sort of represents these functors? So for both of these questions, the short answer is like, yes, we can do it, only if the given scheme is an affine scheme, right? So for question 2, you can just go a bit more and say, if it's a quasi-compact and separated scheme, so you can say that it's an equivalence. For example, affine schemes lives inside. So the broad goal of this seminar is to sort of study the categorified version of both of these questions with the following dictionary in mind. So this I'm not going to go through because we've already seen this in Theo's talk, where he defined this nice correlation between the classical notion and categorified notion. So the idea is like, in this whole seminar, we are going to answer only the question 8.7.01, which is already very illuminating, and it has so much of information from many of the using many of the tools from other areas of mathematics. So just to give a perspective on this question so that it's useful for the next talks. So if we have a connective commutative algebra objects defined on S would be the infinity category of spaces. So if this is a functor and this is the quasi-coherent category of quasi-coherent sheaves. So for a connective infinity ring A, so one can define this natural pullback. So how we define in the normal ring case, you can sort of define it in the infinity ring case. It's just taking the n to its pullback. So this sort of determines a functor called theta. It's exactly defined how, so just theta is exactly mimics how rho A is defined, right? So, but it's just like infinity categorical version somehow. So there's a natural bridge between rho and theta. So we can ask, when is this functor an equivalence of categories? So we will see an answer for this question in the next talks. And the concluding motivation is that, so we are going to, the goal is to sort of reconstruct the Tannaka duality for quasi-coherent stacks. That's sort of the, or more generally, spectral Deligne-Mumford stacks, let's say. So just to have a good recollection, the simplest form of Tannaka duality is that if we have a locally compact topological space, which is represented in this category D, just by knowing the representation of A in D, we can just talk about A itself. So sort of this representation, it's called the fiber functor, and also the it's classically called the fiber functor, but it's also the forgetful functor. It recurs back A. So this we know in the classical setting. And from the last talk, we saw this, how to translate this to algebraic geometric setting, right? So in other words, we just sort of replace the category G by the category of class. G plays G by a stacky version. It's called a classifying stack of a given group G. So the question sort of translates to asking, when is this association a fully faithful embedding? So to this end, we can ask the following question. So we had two questions in the beginning. So the similar questions asked in this improved framework would be, for which algebrogeometric objects one can expect an analog of this question here. So this we know. For example, if the base is an affine base, then we know this is true. Also for some, in cases where the diagonal morphism is affine or the given scheme is quasi-affine, we sort of know some of this data, but then we have no idea, at least now, to see when the analog works. So we're going to see when it actually works. And then, so this is like having a bijection that we have seen before. And then the second question is, how can we characterize those symmetric monadal functors that sort of classifies, that sort of like makes this pull back into a nice package. So for both of these questions, we'll see what is the answer when the value of X is a quasi-geometric or quasi-geometric stack, or quasi-geometric or geometric stack. Sorry, if it's a perfect stack, for example, the notion of locally Noetherian and spectral algebraic spaces, which is like a spectral version of algebraic spaces. And then we'll conclude the whole seminar with how to describing this with the notion of abelian categories. So, all right. So I think this talk would have set some base for the next talks that are about to appear, and I'd be happy to answer any questions. So thanks for your time.
Thank you, Krishna. So, is there any question from the public here or the people online? Okay, so it doesn't seem to be the case, so let's thank Krishna again. And we'll see next week with the next talk of Semiva. Thank you.